Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, number of adjacent elements with same color. The problem is bit easier, but in this particular video, I will be discussing a more harder version of the same problem as well. So stay tuned in the very end. If in case you have already solved this particular version of the problem and are only interested in the follow-up problem, all the timestamps are there in the description down below. You can move back and forth in the particular section you want. With that, let's get started. The problem states that you are given an array nums of length n where initially all elements are uncolored. By uncolored, they mean that all the elements have the value 0. Right now, there are some queries. Each query will be of the form index comma color. Basically, they are saying as a part of ith query, you have to replace the color of index I with the given color I. Right now, you have to return one integer for each queries. So after performing this query or after replacing the color of the index I, you will return the number of adjacent elements with the same color, right? So in other words, what you will say, you will try to find out all the j such that nums of j equals to nums of j plus 1 and nums of j is not equals to 0, right? So let's take an example. Let's say n is 4. So it means that you initially have an array of 4 elements where each of them are initially uncolored or has value 0. Now these are the queries. Let's talk the first query. In this we have 0 comma 2 which says replace the color of 0th index with 2. So we replace the color of 0th index with 2. Now we have to return the count of adjacent elements with the same color. So now you can see how many elements are there such that nums of j is equals to nums of j plus 1 and nums of j not equals to 0. So because the nums of j should not be equals to 0, all these three are already eliminated. So this is the only possible value of j, and you can see this j is not equals to j plus 1, and hence the number of adjacent elements with same color is 0. So for the first one we return 0. Now second query 1 comma 2, you will replace the first index with 2. Now here you will again try to find out the same thing. These two can't be j. These two are the valid values of j. For this particular value of j, nums of j is actually equals to nums of j plus 1. So you found one index. For this particular value of j, nums of j is not equal to nums of j plus 1. So you found only one index which satisfies this criteria, and hence the answer here is 1, right? Similarly, you will keep on doing this and figuring out the answer after each query. So hope the problem statement is clear. Now, how to solve this? So the brute force way would be just to figure out this array, right? And then apply this exact same algorithm to figure out the required result after applying the particular query, right? So the time complexity of this particular solution would be you would be iterating over the entire array to figure out what is the number of adjacent elements which have equal values. So that would take you order and time, right? And you will be doing this for each of the queries. So this will be the final time complexity in that approach, and this would surely not pass because n and q are huge, right? So we need to optimize this. So notice that you can't remove q factor at all because you actually have to iterate over all the elements at least once, right? So we will try to remove this n factor from our complexity. Now what does removing this n factor means, or where from this n factor comes in the first place? This comes because we are trying to iterate over the entire array to figure out the number of adjacent elements which have the same value. Now because we have to remove this, it means we have to somehow figure out the adjacent value or the change in the answer after every query in less than order and time, right? So that's the biggest hint. Let's take an example. Let's say these three are initially ones, right? So this is the state of the array, for example. Now in this case, uh, a new query comes where it says that replace this particular index I with value 2, right? Initially it is 1. Now a query comes that replace it with 2. Now what exactly will be changed in the entire array? This particular position only, right? And because of this particular position, how many indexes in this algorithm would be affected? So this algorithm actually takes care of two things: the current element and the element afterwards, right? So for this particular j, this would be j plus 1. So because j plus 1 actually changed, this particular pair will be affected, right? Similarly, if this was j, this this particular pair would be affected, right? So only two pair of elements are affected. So what we can simply do, for whenever we are updating something, we will first figure out what was its contribution before. So previously this element was contributing to how, because when this was j and this was j plus 1, this this pair contributed 1 to the answer, right? Similarly, when this was j and this was j plus 1, this pair contributed 1 to the answer. Now, because you are saying that it will be changed, it may be the same after changing. Let's say the query was like change I to 1. It may be same afterwards as well, but for simplicity, we are saying that, okay, we will be removing this particular element. So basically, it means whatever the answer we had, we have subtracted 2 from that, right? Because this element is now gone. Now we will simply replace this particular element with the value 2, right? Now after replacing the value 2, we will again try to find out what all changed. So again this pair was affected. So we'll again try to figure out what, like whether this pair currently gives any value or not. So 1 is not equals to 2. So this pair will not give anything to the answer. And the same case is with this. So this pair will also not give anything to the answer. So this would be plus 0. So plus 0 basically denotes that after changing, this number doesn't contribute anything to the answer. So the final output after performing this query would be a minus 2 plus 0, where a was the answer for the array before performing this query. At the very starting point, a would be 0 because initially the entire array is 0, and hence uh, there is no pair that is possible at all. So we'll start with a0 and we'll simply keep on applying this particular algorithm, basically remove the contribution of that particular index and add the new contribution after modifying the element. And finally we will get the output for after the ith query, right? So how the pseudocode would look like? Pseudocode would look like this. We will iterate over all the queries, right? Now we'll check what is the contribution of this particular index in the current array. So how we'll check that? We have two things, right? One is the index before it and one in the index after it. So for index before it, we'll check if index before it exists and the color of them are same, and the index before it, the value doesn't have minus 1 or 0, whatever you call it. And if these two conditions are satisfied, it means this element have contributed 1 to the answer previously. So we'll remove that 1 from the answer. Similarly, you will do the same thing for index plus 1, right? Once you have removed the contribution, now you will simply change the value of the current index. And after changing the value of current index, you will again try to add the contribution of this index. You will do exact same thing if there is a element before this and the color of them are equal. Notice that I am not checking this and color of index minus 1 not equal to 0, because if they are equal, I'm sure that color of index is not 0, because this is what I have updated recently, right? So this is just a small optimization. Basically, we are doing the same thing. We are adding the contribution back after changing the current element. And we will do the same thing for index plus 1 as well. So the entire complexity of this particular solution is we are running over the queries once, and inside these queries we are doing some constant operations. So the entire complexity would be order q, and which would pass the given time constraint, right? Now I'm not sure showing you the code for this because code would be exactly the replica of this particular pseudo code. You can try it out yourself, and if you face any difficulty, feel free to ask them in the comment section below, right? Now comes the interesting part, the follow-up problem. The follow-up problem is given the exact same problem. Like initially you are given an array, everything is zero, and you are given q queries. In each queries you will be given some I comma c, and you will be asked to replace the color of ith index with the value c. Until this part, the problem is still. The problem in the original problem asked for find out the number of adjacent elements with the same color after ith query. This we have modified to we will only consider continuous subarray of the same color and return the largest group after each query or after performing this modification query. So for example, let's say initially everything was 0 and after performing some operation we got this particular array. Now what will be the answer for this array? Answer for this array would be 3. Why? Because there are three elements which which are like which contain adjacent equal numbers or colors. So basically this is the first element for which j and j plus 1 are equal. This is second element, this is third element, and that's it. So there are three elements for which j and j plus 1 are equal, and they notice that there are other elements as well, like for this element and this element as well, j and j plus 1 are equal, but we need to only consider one particular color. Which color we have to consider is something you have to figure out. Basically you have to figure the optimal color that will give you the best possible answer. That is the problem. So here you can see there is you could have taken one as well, and if you have taken one you will get a value of 2, but because you have taken 2 and this particular range, you got the value 3, right? So which range to pick and what will be the value or which color to pick, all those things you have to figure out by yourself as a part of the query and return the largest possible answer, right? So if the problem statement is clear, I would encourage you to pause the video right away and try to think about this version of the problem by yourself for a bit. So coming to solution, what is the first solution that comes to your mind? Again, we'll start with brute force only. So the first solution that you can try is you will iterate over the entire array, right? And figure out the array, like divide the array into groups. Let's say you divide, okay, you say I found there is one group which contain 1, 2. Now for this group, what will be the answer? Answer would be 0, right? Now you say, okay, I will move forward. I found another group of 1 of size 2. So the answer for this group would be 1, right? You will move forward. You will find another group and you will say answer for this group is 3. You will find another group. Answer for this group is 2. Move forward. You will get 3. Answer for this one is 0. Now finally you get this particular group and answer for this would be 2. Now at the end you can iterate over this answer for each of the group and return the largest particular group, right? So this is one possible way to find out what is the required answer after you have modified the array, right? And so what is the time complexity of this particular approach? For each query you are iterating over the entire array, so the complexity is again order n into q. But this is something we want to optimize on. We also want to solve it in n log n or n root n or anything of that sort. So would again encourage you to pause and try to think by yourself. So let's move ahead. The thing is you are finding out these ranges, right? So we have to somehow maintain these the ranges or the values of the groups somewhere in a data structure, right? So let's say you maintained the group sizes in a data structure, right? Now, now a query comes that okay, replace this particular 2 with 3, right? What will you do? Notice our motive is again to remove one of these factor, and again we can't remove q because we have to iterate over entire query at least once. So we will try to remove n or replace n with some logarithmic factor of n, right? So that's what our motive is. We will apply the exact same trick. Basically, we'll say, okay, we know that we are changing one element, and this change only affects two things, right? So we will apply exact same trick here as well. So we say, okay, we change this particular index to 3. Now, what all will change here? So previously, this was the complete group, right? Now there will be three smaller groups. One is this, second one will be this, and third one will be this, right? So what will happen? This 4 is now broken down into three pieces: 2, 1, and 2. Sorry, 1, right? Now, if you are able to do this efficiently, if you are able to figure out that you have to break 4 into 3 part, and if you are able to do this efficiently, the problem is solved, right? Now, how exactly you will figure out that these two is a part of a group which is of size 4? If you are able to figure out this, then you can simply break that particular group because you know the start and end of that particular group, right? So once you figure out the start and end of the group where this element I belongs to, you can simply split those groups and rearrange the values here, right? So what you need to know, we need to know what which group index I is a part of, right? So for this we need to somehow also maintain the left and right ranges of each of the groups, right? And then only we will say, okay, where I lies. So we'll say, okay, these are the left and right ranges of each of the groups, right? 0 0 is one group which contains, like, which is filled with color 2. 1 2 is one group which filled with color 1. Similarly, 3 6, this entire one is filled with color 2, and so on and so forth, right? Now, when you get a query for particular I, let's say you get a query for 5, I equals to 5, you will search in this list, you will figure out the particular group where 5 will belong to, right? And once you figure out this particular group, you know what is the value of L and R, and you also know what is the color of these all elements. So this will be 2. Sorry for that. You also know what will be the color of these elements, right? Now, what, like, how exactly will you find this is something we'll come to later. But for now, we know what is the group of I, what all, well, like what is the color in which I is filled with. So we can simply go here and update these values. Now notice that we can update this 4 easily, but we also have to update this particular data structure as well, because we have maintained a new data structure, so we have to maintain it as well. So this 3 comma 6 is now removed, and instead of 3 comma 6 we have three groups. One is 3 comma 4, another one is 4 5 comma 5, another one is 6 comma 6. So 3 comma 4 is actually filled with 2, right? Similarly, 5 comma 5 is actually filled with 3, and finally 6 comma 6 is actually filled with 2. So in place of this single group, you will now have these three groups, right? So this is what we have to do. If we are able to again maintain these two data structures efficiently, we can simply ask this data structure to give me the maximum element it has, and that will be my answer, right? And what exact data structure will you use here? You know, you have to erase an element, you have to insert an element, and you also need to know what is the largest element here. So you can use set or heap. If you're using set, notice that there can be duplicates. So you have to use multiset as well, right? So this data structure would be multiset. And what about this? How will you maintain this data structure? This data structure, what we are doing, we are inserting elements, right? We are also erasing elements, and we are also doing a search. Now this search you can either do linearly or you can use binary search, because you can just keep the elements sorted and do a binary search. Now which one of the linear or binary search will you prefer? The thing is, if you do linear search, this will again be boiled down to order n, right? Because in the worst case, each element would be its own group. So there can be n elements in this particular array, and your search would take order n time. So we will always try to keep this array sorted and try to do binary search. So what all things we need to perform in this data structure? We have to erase an element, we have to insert an element, and we have to do a binary search. Again, the best data here is set. You will, or any kind of balanced binary search tree, right? So we will have one set, we will have one multi-set, and we will just keep maintaining these two for each operations we are performing. And to get the answer, we can simply query what is the maximum in the second data structure, right? Now let's iterate over one more example for one last time, and we will look at the pseudo code for this thing, right? So let's say now you are asked to remove this particular element with a value 1, right? Now what will you do? You will first figure out which group this 3 belongs to. You will again do a binary search here. You will land at this particular index, because this the value of the index of this particular element is 10, right? So you will land at here. Now sorry for this is again 1, right? So you will land here, and here the value is 3. You will want to change this to 1, right? So what you will do, again you will erase this is 1. So you will erase this particular element, right? As soon as you erase this, you will also erase this particular element, because this is no longer exist now. Now what you will say, okay, I will try to divide it into 3 parts again, but notice that there is only one index here, so you can't divide into 3 parts. Instead, you know that the leftmost part of this range is colliding with the index I, right? Leftmost part is 10, and 10 is colliding with I. And because you are changing I, it might happen now that it can get merged to the previous element, right? Initially it was 3, and because it was 3, it is separated from the previous group. But now you are changing this 3 to something. Now if this something is equals to the previous group's element, then we can simply merge the previous group and the current group, right? So that is one extra thing that we need to take care of. Basically, whenever we are inserting any range, we will just make sure that the range before it can be merged or not. So in this particular case, we'll say the previous range is 7 comma 9, which contain 1, and because we are also replacing this current value with 1, so these both are matching. So we will, what we will say, we'll say okay, remove this range as well, right? Now everything from 7 to 10 will be inserted in a single range. Again, you will see, okay, R is also colliding with I. It means the rightmost endpoint was which was keeping the next group separated from 3 is also colliding with I. And because I is changing, the rightmost group might also change or might also be merged. So you will again do the same thing for the R part as well. You will see the next element. If next element is equal, it means you can merge this with the current range as well. So you will remove this one as well, and you will say, okay, my new R would be this. So this will be the new R. So this will be the new L, this will be the new R. And finally, you will insert one single range. Now, before inserting, you will also remove these things, right? Because these two data structures should be in sync, right? And finally, you will insert a new range, which is L comma R comma 1. Here L is 7, R is 13, and the value is 1, right? So you will insert this range, and corresponding to this, you will also insert here a value here. So you will insert 6 here, right? 6 or 7, whatever you want. Like, I think you will figure out that. So this is how you will keep these two data structures in sync every time, right? So hope you understand the solution completely. The time complexity is, you are what you are doing, you are removing some elements and you are inserting some more elements. So how many elements you will be inserting in the worst case? There are q queries, so you will be inserting at most q elements, right? Or n plus q elements, to be precise. And in the not n plus q, I think only q elements, right? Because in each initially you will have only one range, because everything is zero, right? Now, as and when query comes, you will be dividing this, and the worst case is, for each query, you will be dividing this range into three parts. That's the worst case, right? So in each query, you might be inserting three new ranges. So you are inserting three q ranges, right? And because you are inserting three q ranges over the lifetime, you can only remove three q ranges. So basically, you are doing three q inserts, three q removals, and three q binary search. And you are also doing the same with this data structure. So basically, everything here is log n. So the final complexity is order 3, like order q log q or q log n, whatever you call it, right? So let's look at the pseudocode. The pseudocode is exactly similar to what we have just discussed. So we have this group structure that we have created, which is like, which contain the left, right, and the color of a particular group. And as discussed, we will have two data structures. One is the set of groups, and second is the multi-set of integers, which only contain the group sizes. Initially, we will insert everything 0 to n minus 1 as 0 in this particular group. Now, as and when queries come, we will try to find out the group of the current index, right? How to find a group of the current index? You will just do a simple binary search, upper bound and minus minus, or a lower bound with uh, some plus, sometimes plus plus. So once you figure out the current group, you will see what all you need to insert and what all you need to erase, right? Notice that you may need to erase multiples and you may need to insert multiples as well. So one important thing that you should take care while having set or any kind of data structure is, you should not remove and insert at the same time, right? So let's say you erase this current group at this particular step itself, then it will not point to the right pointer, right? So that's why whenever you are dealing with any data structure where you have to maintain some kind of pointers, always keep all the insertion and deletion at the end, or in other words, always keep the mutations at the end. First query as much as you can and then do all the mutations. So that's why we are saving all the mutations so that we can apply it at the end, right? Now, what all we need to insert? Again, we will simply see if the left range coincides with the current index or not. If it is not coinciding with the current index, then it is simple. Basically, what we are saying, that L is not changing. And because L is not changing, it can't be merged with the L minus 1, right? So we'll just simply insert a new group which will start at that, like, previous L and end at index minus 1, right? Otherwise, L is actually changing, right? And because L is changing, it might be merged with the previous L as well. So we will try to merge it with the previous iterator. And now, because we haven't deleted anything, IT will point to the current element. We can simply do IT minus minus and we'll reach the previous value. And if it is matching, we will update the new L and we will also insert the group to the erase. Notice that we will not simply erase because erosion, like all the mutations, we are saving it for the last. In the very same fashion, we will look for the right side as well. If right side doesn't coincide with the index or right side is not changing, it means we can't really merge anything on the right. So we'll simply insert this particular thing. Otherwise, right side is changing, so we'll try to merge the forward element and update new R this time and also erase anything if required, right? If it matchings. Now finally, after doing this, we know what all to insert and what all to erase. We'll simply insert those and erase as well. And finally, result would be the max in the group size. Now how to find max? You can simply do set.end minus minus. That will give you the maximum value, right? So hope this entire solution makes sense. I would strongly encourage you to pause the video and try to code this entire solution by yourself. Next, we're looking at the code. Now, if you want to verify your code, whether your code is correct or not, what you can do, I can give you a small sample and you can try to, like this sample consists of everything. Basically, it will have scenarios where this kind of things will be applied. It will have scenarios where you have to divide into three. It will have scenarios where nothing is changed, and so on and so forth. So basically, you can try running your code against this sample. I will paste them in the description section below. You can check them out and try to print out the values of the sets and the values of the two data sets by yourself. And if those values are correct, you can simply assume that your algorithm is correct. Or even simpler, you can copy paste this code, figure out uh, figure out the output for this particular input and match it with your output, right? So the code is exactly similar to the pseudo code that we have looked at. This is the group. It contains LR and color. And we have overrated less than operator because we are using a set of groups. We want this group to be sorted by L. So that's why we have sorted this with L. Now inside this we are maintaining, like initially we are clearing out these two things because these are kind of global variables, and we insert -1 to n. Now why -1 to n? That is an implementation detail. Basically, I don't want to deal with s dot begin minus minus or s dot end and so on and so forth. So basically, I inserted one element before and one element after. So that is a simple trick that sometimes helps. Now, after this, we are iterating over all the queries as we discussed. We find out the current index, we figure out the current group, and if current group color is actually equals to the new color, it means nothing will change. So we'll just simply continue, right? If that's not the case, it means the color is actually changing. So again, you can remove this if condition completely. This is just for testing purpose. Um, After that, you can figure out what all need you erase, what all you need to insert. So for that, you can like these are the three new groups that could have been formed. Now you will see which one of these three groups you will be inserting, or you will be creating, merging the groups with the previous groups as well. So same thing, we'll check if index is not equals, if not touching with the left part. So basically L is changing or not. If it is not, we'll simply insert L1 and R1 and C1. Basically current group L with index -1. Same goes for the R part as well. Otherwise, as discussed, we will move to the previous iterator. Now I put here while, but this can be feasible, right? That doesn't matter. So you will simply figure out the previous element and insert it to two arrays and also update L2. This L2 is nothing but new L in this pseudocode. Now, after like you will do the same exact thing for the like right part as well, and after that you will insert the new group L2, R2, and C2. Finally, whatever you want to erase, you will erase it. Whatever you want to insert, you will insert it, and you will push the current answer to to the result. Now, what does erase and insert function look like? Notice that we have to update two data structures at once. So that's why I've just merged these two things in an insert function so that I don't forget to update one of them while updating the other one. Similarly, for erase, I'm doing the same thing. One extra thing is here, because we are erasing a particular number and the given set is a multi-set, we have to make sure that we erase the number only once. And that's why we find the number first and then erase that particular pointer, right? And this get answer is simple as we discussed. We'll just do dot and minus minus and get that particular value, right? So hope this entire session makes sense and hope you enjoyed this particular follow-up. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.